SPH4U, wave nature of light. 5.3 single and multiple slit interference. So first we're going to discuss Young's double slit experiment. So if light is a wave, then light should be brighter in areas of constructive interference and darker in areas of destructive interference. So if two waves arrive in phase, they would create constructive interference. And if two waves arrive out of phase, they create destructive interference, as we saw in last lesson. So Thomas Young got two light sources in phase and made the distance between them small enough that a series of light and dark bands were created on a screen placed at the back of the box wherein this experiment took place. So this screen was light sensitive and it created light and dark bands, which are called interference fringes, or maxima, which are antinodal, and minima, which are nodal. And these maxima were light, while these minima were dark. So here's a visualization of this double slit experiment. So S1, S2, these represent the two sources of the light. So D, this is the distance between them. Distance between light sources. So L, that is the distance from light sources to screen. So this delta x, that is the distance of the point that you're analyzing in this scenario from the central maximum. And lambda, that is of course the wavelength of the light. So all of these can be put together to create this equation. Delta x over L is equal to lambda over D. Alright, so here's three diagrams displaying double slit interference. So in this first diagram, we have these two waves which are in phase. Here, I'll light this in blue. In phase. So as they're in phase, their path difference is 0. So they create constructive interference at point P. So this is the central maximum, and this is bright. So constructive interference, and it's bright. So here in the second diagram, these are not in phase. So when they're not in phase, this wave, it has a maximum here, while this phase has a minimum. So this creates destructive interference, and this is dark. So this is dark. And the path difference, as you can see, they're 1/2 lambda apart. So this creates this destructive interference because they're no longer in phase. So in this diagram, we can see that both the waves, both of their minima meet up at this point P. So this means that they are in phase. So this is constructive interference. So this is a bright spot as well. And then it'll have another area of destructive interference, so that will be dark, and then it'll continue alternating. So when there is an area of light and bright light, then the two waves, they are in phase. When it's dark, the two waves are not in phase, and they are destructive in their interference pattern. Alright, so here are the equations for double slit interference. So for nodal lines, or destructive interference, we have this equation. Sine of theta is equal to n minus 1/2, so n is the nodal number, times lambda over d. So n can be 1, 2, 3, etc. So for antinodal lines, is called constructive interference. And it's given by this equation. Sine theta is equal to m, so m is the antinodal number, times lambda all over d. So m is equal to 1, 2, 3, etc. That will be given in the question. So here's an example of double slit interference. So two slits are separated by 21.6 micrometers and are 3 meters away from a screen. The fifth nodal line is 37.5 centimeters away from the center of the interference pattern. So what is the wavelength? So we know that n is equal to 5 because it's the fifth nodal line. So the slit separation, you had to convert that to meters, so that's 2.16 times 10 to the negative 5 meters. So they're 3 meters away from the screen, so big L is 3 meters. So fifth nodal line, and the fifth nodal line is 37.5 centimeters away from the center of the interference pattern, so that's 0.375 meters. So what is the wavelength? So we have the equation dx over L is equal to lambda over d. So this is actually equivalent to sine theta, which is also equivalent to n minus 1/2 times lambda over d, which we learned last time. So we can figure out the lambda using the nodal number with this equation. Dx over L is equal to n minus 1/2 lambda over d. So now we just use algebra to solve for lambda. So delta x times d over L times n minus 1/2 is equal to lambda. So in order to find lambda, let's just sub in all these numbers. So 0.375 times 2.16 times 10 to the negative 5 over 5 times 5 minus half. So lambda is equal to 6.00 times 10 to the negative 7 meters. So here's an example of another double slit interference question. So a third order dark fringe of 652 nanometer light is observed at an angle of 15 degrees. So what's the distance between the slits? So we know the equation sine theta is equal to n minus 1/2 times lambda over d. So we need to solve for d. So sine theta over n minus 1/2 d is equal to lambda. So d is thus equal to lambda times n minus 1/2 over sine theta. So d is equal to 6.52 times 10 to the negative 7, so we converted it out of nanometers, times 2.5. 2.5 is the 3 minus a half, and all this is over sine of 15. So distance between the two slits, it comes out to be 6.3 times 10 to the negative 6 meters. So now we're going to go on to single slit interference. So this is kind of like the diffraction patterns of water that we discussed in the first lesson of this unit. So narrow slit, the higher the diffraction. So here the central maximum is the brightest, with the following maximums being less and less bright. So the pattern on the screen at the back, it looks something like this. So this is single slit. So as you can see here, the central maximum is the brightest. And they get progressively less and less bright as they go away from the central maximum. So this is compared to the double slit, where all of them are of basically equal brightness. So here are the equations for single slit interference. So for the maximum, we have sine theta is equal to m plus 1 half times lambda over w. So this is the bright areas. And this w is the width of the central maximum. For minimum, we have sine of theta is equal to n times lambda over w. So these are dark areas. So this is an example of a question that deals with single slit interference. So visible light of a wavelength 550 nanometers falls on a single slit and produces a second diffraction minimum at an angle of 45 degrees relative to the incident direction of the light. So if this is our slit and we have the screen here, this is the second minimum, and this is the incident direction, this is the 45 degrees. So what is the width of the slit? So we have this equation, sine theta is equal to n lambda over w. So we need to solve for w, so we rearrange using algebra. So w is equal to n times lambda over sine of theta. So that's equal to 2. So 2 is n times lambda. So wavelength is 550 nanometers. So in meters, that's 5.5 times 10 to the negative 7 meters. So 5.5 times 10 to the negative 7 over sine of theta. So over sine of 45. So this comes out to be 1.56 times 10 to the negative 6 meters. That's the width of the slit. And now we have the question, at what angle is the first minimum produced? So for this, we use the same equation, sine theta is equal to n lambda over w. So therefore, theta is equal to sine inverse of n times lambda over w. So theta is equal to sine inverse of 1. So this is the first minimum, so it's 1, not 2. Times 5.5 times 10 to the negative 7. All this over w, so that's the 1.56 times 10 to the negative 6 that we got from before. So this comes out to be 21 degrees. So that's the angle at which the first minimum is produced. Diffraction grades have a very large amount of equally spaced parallel lines which act as individual light sources. So since there's such a high amount of lines, these lines of light are very sharp and very bright. So for an example, at what angle will 638 nanometer light produce the second order maximum when passing through a grading of 900 lines per centimeter? So we know that lambda is equal to 6.38 times 10 to the negative 7 meters. So for D, we know there's 900 lines per centimeter, so we flip it. 1 centimeter per 900 lines, so this comes out to be 1.11 times 10 to the negative 5 meters per line. And we know that m is 2, so we have this equation, sine theta is equal to m lambda over d. So theta is equal to sine inverse of m, which is 2, times lambda, which is 6.38, times 10 to the negative 7, all over 1.11 times 10 to the negative 5. So theta comes out to be 6.6 degrees. There we go.